Good afternoon. Put your pencils down and pick up your colored pens. Get ready to grade your work and correct your work if necessary. Also be ready to support your answers with logical reasoning. We will be using the equity bars today, so stay on your toes. You will be called on randomly. So let's see how we did. And remember, this is a safe place to make a mistake. It's no big deal, as long as you're making an effort. If you make a mistake because you're just sitting there doing nothing, that's it. So let's see how we did. Number one, I'm looking for the values of x and y. Let's start with student number 15, student number 2, and student number 7. Student number 15, what'd you get?
X equals 20.5 and y equals 6.
Okay, student number 2, what did you get?
X equals 20.5 and y equals 6.
So you agree with Sebastian. Student number 7, what did you get?
X equals 20.5 and y equals 6.
So 3 people agree, and they happen to be correct. So I know 3 people got the right answer. We'll sort of survey the whole group in a few minutes. Number 2. Start with student number 8, then student number 9, and then student number 17. Student number 8, what did you get for x and y?
X equals 8 and y equals 3.
Okay, student number 9, what did you get?
X equals 8 and y equals 3.
So you agree, and student number 17. Okay, well I appreciate your honesty. X equals 8, y equals 3. So these were interesting, challenging little puzzles that you had to kind of piece together. And it's not a proof, but you needed a path of logic to get yourself to what I was asking for. So let's start with number 1. How did you begin? How did you begin? Nathaniel, how did you begin? Number 1.
I saw that 8y minus 7 is equal to 6y plus 5. And so I paired them together and solved it. So I could get y equals 6.
Okay, I love how you described that. That was beautiful. That he recognized 8y minus 7 was congruent to 6y plus 5 because of the arc marks. Made an equation setting them equal to each other and got y equals 6. So I want to say that I feel like everyone in the room should have been able to do that part. And it was great explanation that he gave. I think the next part was a little bit more challenging. So let's hear about how you got to the 20.5. How did you accomplish that? Start with Alexandra, and then we're going to go back to Kamoy.
I found measurements of two. I never mind. It's bad at explaining stuff.
Actually, you're doing quite well.
No,
You just
I don't know what to call them. I don't.
so make reference to where they are. The 2 angles.
The 2 angles with the arc marks.
Okay, wonderful. That wasn't that hard. So you found the measurements of them. What were the measurements?
41 degrees.
Okay, and you accomplished that how?
Plugging in the y.
Okay, so you plugged in 6 here, and you got this is 41 degrees. And you got that was 41 degrees. Very good. And what did you do after that?
Since all angles have equal 180, I added them, subtracted from 180 to 99.
Okay, so you got the third angle of the triangle. And what is the third angle? So this was 98 degrees right here. Okay, what reason could you give for that? You kind of explained it, but there's an actual theorem or postulate that supports it. How can we get this when we have that and that?
Third angles theorem.
Very good, the third angles theorem, very good. So the third angles theorem allows us to get the 98. Give me a thumbs up if you did what she did. Good, extolled. After you got the 98, what'd you do? Let's say the triangle on the left and the triangle on the right.
The triangle on the left, yeah, on the base angles, they're congruent because
I love where this is going.
the base angles theorem.
Okay, well that A is not supposed to be there.
And
Okay, so you know that this is congruent to this, so you know that that's 4x, so that must be 4x, okay?
then subtract 98 from 180 will be a 4x.
Why? Why subtract it from 180?
You're linear.
Ah, because it's a linear pair with this angle right here. So subtract it from 180, we get this value. But then if we set it equal to 4x, we can find x because that's what I asked for. I asked for x, not the actual measurement of the angle. Very nice. Very nice path of logic. There was actually a path of logic that saved you a step. Did anyone figure out the way to do it where you could skip over that step right there? What is this angle called in relation to this object? That angle has a name. What is it called? John? No, transversal has a line that goes across two other lines, so I appreciate the effort and the guess, but that's not even in the ballpark. Zumar? That's the exterior angle. Starting to ring a bell. It should. There is a relationship between this angle and these two angles. What is the relationship between those? Kadir?
Some of those two angles, 41 angles, should equal that angle, the other.
Yeah, it's called the exterior angles theorem. The exterior angle theorem or something like that. This angle will equal the sum of these two. So I appreciate that you guys use the third angles theorem to get this and then use the linear pair to get that, but you could have skipped over that. If you had known the exterior angles theorem, it tells you that that is going to equal the sum of that and that. So we knew that that was going to be 82. I don't care either way. Both are wonderful. Does anyone have any questions on how we accomplished number one? Okay, let's take a look at number two. I would say that for one reason, number two was maybe a little more challenging than number one, but it's just an opinion. And there was a detail that you had to remember, think of, realize to even get started. So let's first take a survey. Give me a thumbs up if you got number two correct. Okay, good. Put your thumbs down. Kalasia, what detail did you have to realize to make it work? That was exactly it. You had to remember that all the angles in an equilateral triangle are 60 degrees. Which means this is 60 degrees, but you're also given this right angle symbol right there. Which means this whole angle is 90. if the whole angle is 90 and this part of it is 60, what's the measurement of this little part left over? Sharik? 30. This must be 30, which means 4x minus 2 must equal 30. So I don't think the path of logic is as complicated as number 1, but I think that you had to realize that piece of information, that this was 60 degrees, just to even get started. Whereas in number 1, the starting point was much easier to see, that these two were congruent, set them equal to each other, and you solve for y. So once you solve this and you get your x, then you can figure out the measurement of this angle, because this angle is going to be congruent to this one because this is an isosceles triangle. This tells you that that is congruent to that. So then you can figure out y from there. Any questions about that? Very good job, Kalasia, and I know there was some other people who figured it out. Any comments, questions, or concerns? Nothing at all? Good, I appreciate the high level of effort. I really appreciate what I saw during the warm-up, people trying to explain to their teammates what was going on and referring to this triangle and that triangle and trying to point out the different relationships. I really appreciated that. That was very good. So let's pause here. So yesterday I reflected on the chapter as a whole, and we spent the majority of the time talking about triangles and how to prove them congruent. But we also took a quick little side trip towards the beginning of the chapter in which we introduced the idea of transformations. And we're going to go back to that today. We're basically going to take what we learned with transformations a couple weeks ago and kind of wrap it together with what we've been learning about triangles and their congruence. So, our objective today is to be able to draw, identify, and be able to work with different transformations in the coordinate plane, which we introduced a couple of weeks ago. Here's some vocabulary that you already know, and then a couple that you don't know. Reflection, rotation, translation. You should already know that those are different types of transformations. There was also another phrase that I introduced to you. Does anyone remember the phrase that described a type of transformation that kept the shape the same? It's been a while since we used the term. It was rigid motion. So I introduced the idea of rigid motion, and we're going to revisit that idea with a different name. And we're calling it now a congruence transformation, where we transform an object but maintain its congruence. These are the different ways of doing it. A reflection, a rotation, and a translation are called rigid motions, and they are also called congruence transformations. You are also going to be introduced to something. You've already seen it before. It was actually on the Baths test, and I think you've seen it throughout the book a few times. And Sharik, is called coordinate notation, and you're going to learn how to work with that today. So, first of all, a review of what you know. Of course, if it's things you already know, you don't need to recopy it. But a transformation is when we do something to a figure to transform it in some way. The new figure is called the image. Does anyone remember what the starting picture was called? It was a little bit of an unusual scenario. The new object was called the image. What was it called before it was the new? John? It's called the pre-image. So we go from a pre-image to an image. Here are the three types that we just touched on. A translation is a slide. It moves every point of the figure either right, left, up, or down. A reflection uses a line as a mirror. A rotation turns a figure about a point, a certain number of degrees. All three of these will maintain congruence. In other words, the shape won't grow or shrink. There is a type of transformation that won't maintain congruence. It's called a dilation. We're not studying it today. So, that leads us to the new material. A congruence transformation changes the position, but it doesn't change its size or shape. And that's what we touched on again. That's rigid motion will perform a congruence transformation. Any questions about the terminology so far? All right, so let's get into the notation. Coordinate notation. And now you're going to see this starting today. You'll see it periodically throughout the year. You're going to start seeing, and I'm going to get to specifics, but I first want to focus on this. That's an example of coordinate notation. This is the starting ordered pair. That means transformation. And this is the rule that we use to transform the original figure, or transform each point. So what happens is that an original point, something happens to that original point, and it becomes a new point. So, the one that I've highlighted here is the coordinate notation for a translation. A translation will add a number to the x and will add a number to the y. That will translate it. A reflection is quite simple, actually. You keep everything the same except you flip the sign of the y coordinate, and that will actually reflect it over the x-axis. So this is the coordinate notation for a reflection in the x-axis. Sounds a little counterintuitive, but when you see it, you'll understand. And then the coordinate notation for a reflection in the y-axis, similarly, everything stays the same except you flip the sign of the x value, and that will actually reflect it across the y-axis. Now, you're going to see some rotations in your homework, but I'm not going to touch on rotation in the lesson because you don't use coordinate notation for rotations. Rotations are a little bit different. Okay? Any questions so far about coordinate notation? Now we're going to start using it. So what we're going to be doing is drawing some figures and moving them and transforming them. Okay, so we're going to, of course, you're using graph paper. It's going to make it easy. So let's jump in and do a transformation. So, figure ABCD has these vertices. Sketch the figure and its image after the translation, and here is the translation that we are to use. So this is the rule that tells us how to transform it. So, we can start by drawing the original figure, the pre-image, or we could start by figuring out what the new image is going to be. We can go in any order that we want. I would like to start with the original image this time. So we need a coordinate grid. So go ahead and set one up for yourself. I'm going to set one up for myself. And we're going to draw the pre-image, A, B, C, D. So we're going to work simultaneously for a couple minutes. And make sure you label your points. So we're going to go -4, 1, 2, 3, 4, +3. That's point A. -2, 4, 1, 2, 1, 2, 3, 4. That's point B. Point C is -1, +1. And point D is -3, 1. 1, 2, 3. And we are going to connect the dots to form a figure. So do your best to accurately connect. And as I indicated already, we want to label A, B, C, D. Does anyone have any questions about how we put that together? That's pretty basic. I mean, that goes back to week 1. Actually, it goes back to last year. Okay, so we've got a figure. Now we want the transformation. So, what we do is we take each ordered pair, plug it into this rule, and get a new ordered pair, and that becomes part of the new image. So, let's start with A. A is -4, 3. That's going to transform by using this rule. We add 5 to the x-coordinate. -4 plus 5, we get 1. So our new point is going to be 1, something. We get the y-coordinate by subtracting 2 from it. So 3 minus 2 is 1. That has a name. Now, if the question doesn't tell you the new letters, you call them prime. You call them A prime, and this is what it looks like. You just put a little apostrophe next to it. That's read A prime. So A prime is 1, 1. You actually saw that on the BAFs. I was told by one of your peers that it actually had A double prime on one of the questions on the BAFs. That's a second transformation. So we've now translated this to this. So I'm going to plot this first one just so we can see what's going on. So now 1, 1 is right there, and that is A prime. So this, using this rule, ended up over there. Does anyone have any questions on how we did that? So now we're going to do that with all the points. Point B, C, and D. So point B, -2, 4. That's going to transform into add 5 to the x, subtract 2 from the y. Add 5, we get 3. Subtract 2, we get 2. And that will be called B prime. Point C is -1, 1. That's going to transform. Add 5, we get 4. And subtract 2, we get -1, and that's C prime. And point D, I'm going to move over a little bit so I can fit it in. Point D is -3, 1. And that's going to transform into add 5, we get 2. Subtract 2, we get -1. And that will be called D prime. Plot all the points. 3, 2. 4, -1. And 2, -1. Connect the dots. and label your points. And so now, using coordinate notation, we have transformed ABCD to A prime, B prime, C prime, D prime. And this is a congruence transformation because we moved the shape, but we didn't change, we moved the figure, but we didn't change the shape and we didn't change its size. Any questions about what we did here? Any concerns? Okay, nothing at all? All right, so let's take a look at a different one. So what will happen with a reflection? So I have an original picture here. I'm going to redraw it. You're going to draw it yourself. So we need a coordinate grid set up again. Let's see, how many do I need? 1, 2, 4. So again, we're working simultaneously right now. And so now let's just sketch the picture. So it starts at -1 on the x-axis, and it looks like it goes up 2. So let's start there and go up 2. And then it goes across 2. So we're going to go from there across 2. And then it goes up another 2. And from there it goes diagonally to 1, 2, 3, 4, 5 on the x-axis. So let's see, 1, 2, 3, 4, 5. It's going to go all the way to there. Any questions on what we just did? I mean, we just basically recreated the picture. So now we want to reflect it using the x-axis as the mirror. How could we do that? How could we accomplish that goal? Did you already do it? Some of you very quietly working. I don't know if you go ahead or behind or what. How could we accomplish that? How could we reflect it over the x-axis? What would we have to do? Kadir? Okay. So we can look at the vertices. Okay, absolutely. Could you give me the coordinates of one of them? -1, 0. So right there. Okay. Good. Anyone have a different idea of how we could reflect it? John? Okay, so we can literally just draw it going the other direction. But we're actually going to do both because we want to see what happens to the coordinates when we do a reflection. But we're going to use John's approach first, and then we're actually going to go to Kadir's approach. So now I don't need this. Now I just want the reflection. So, do what John said. If we went 2 up, now we have to start here and go 2 down. And if we went 2 across before, now we have to go 2 across from here. We went 2 up from there, now we have to go 2 down. And then again, connect it to 5 on the x-axis. And we should end up with a perfect reflection. Does anyone have any questions about how we did that? But now let's explore what Kadir referred to, the vertices. So he said one vertex was here, but it's the same because it's when you reflect it, it's actually staying in the same spot. Let's look at this vertex right there. What are the coordinates of that point? Come on. -1, comma 2. Let's look at its corresponding point in the reflection, which is down here. What are the coordinates of the green one that I just drew? Stephen? It's -1, comma -2. So look at what happened. It's the exact same coordinates except the y coordinate flipped sign. So the y coordinates are opposite, but the x coordinates are the same. Let's do another one and see if that pattern continues. Let's look at this vertex right up here. What are the coordinates of that vertex? Only 3 people can tell me the coordinates? Go ahead, Stephanie. 1, comma 4. Let's look at the corresponding vertex in the reflection, which is down here. What are the coordinates of that point? I'm sorry, so let me ask it differently. Give me a thumbs up if you know the coordinates of that point. Okay, Eric, what are the coordinates?
1,
Good, 1, comma -4. So once again, you see the pattern continued. We had a 4 and the sign flipped while the x coordinates stayed the same. That will actually be true no matter what point we pick here. Its corresponding point in the reflection will be the exact same coordinates except the y coordinate will be flipped. Okay? So if I pick this point, then go to its corresponding point, it will be the exact same coordinates with an opposite y. If I pick this point, same thing will happen. If we pick this point, same thing will happen. Anyone have any questions about that? So that is what is meant when I introduce this idea, that for a reflection about the x-axis, x comma y transforms into x comma -y. That will reflect something over the x-axis. Does anyone have any questions about that? Any questions at all? Checkpoint number 1. Now I'm going to ask you to do something that we haven't done yet. Well, we have actually, but not quite this way. So now the vertices of triangle ABC are given to you. A translation of triangle ABC results in the triangle DEF. So now I'm giving you new letters. And I'm giving you the new coordinates. But now I want you to tell me what rule made the transformation work. So you have to tell me what transformation made triangle ABC transform to triangle DEF. You got 2 minutes. If you're confused, you ask a teammate. If you're still confused, you ask me. Best choice, you do it completely on your own. Second best choice, you do it with a little assistance from teammates. Third best choice, you do it with assistance from me. 30 seconds, team talk, and compare what you wrote with your teammates.
I'm the best. I can't understand. I actually did.
Okay, give me a thumbs up if you and your teammates agreed on the coordinate notation. You agreed, you agreed, you agreed, you agreed, you agreed. You don't agree that you agreed.
No, we do.
You do agree. Okay, so everybody seems to agree. Okay, so Kayla, what did your team agree on?
X plus 1 and y minus 1.
Okay, Extol, what did your team agree on? So the coordinate notation is x plus 1, y minus 1. Any questions on how we accomplish that? So I only asked 2 teams. Give me a thumbs up if you and your teammates got it right. Good, that's what I thought. Put your thumbs down. So now we're going to take this idea and wrap it with what we've been working on the whole chapter, which is congruent triangles. So now we're going to add one element. That title is not supposed to be there. That's my mistake. So we have a triangle, ABC. Here are the vertices. We have coordinate notation that describes a translation to another triangle, DEF. So we're going to do that. But here's the element that we're going to add in. We want to prove that the 2 triangles are still congruent. So we want to be able to use what we know from this whole chapter to prove that the transformation was a congruence transformation. So first we're going to do what we've been doing so far today. Then we're going to add this element of proving it. Okay? It's all stuff you already know how to do. We're just, again, wrapping it together. So we need another coordinate grid. So go ahead and get one set up. I'm going to get one set up for myself. Let's see, how far do I need to go? 7. And we need both triangles, so we need ABC, and then we need to do the transformation to get DEF. So let's work simultaneously. So we're going to just work at the same time, and I'm going to talk through what I'm doing as I'm doing it. So first I'm going to plot the points for triangle ABC. 4, 4, right there. 6, 6, right there. And 7, 4, right there. And I'm going to connect the dots to form the triangle. Now we need the transformation. And now I'm going to talk to you about trust and my expectations as far as you guys. Some of you could do the transformation mentally. Some of you can't. I'm going to leave it up to you to decide how you want to organize yourself. I tend to get a little bit lost when there's lots of numbers that I have to deal with. If it's only a couple, I could do things mentally. If it's more than that, I might need a little more organization. So it's kind of up to you. In other words, do you want to write down this? Do you want to write down that A is going to transform into D which is going to be 5, 1? Or can you do that mentally? Do you want to do it all at once? Or do you want to do one at a time? I leave it up to you. You decide. I'm going to do it all at once here. But one way or another, we need the new triangle. So B is 6, 6, and that's going to transform into 7, 3. And point C is 7, 4. And that's going to transform into 8, 1. Now I need to plot DEF. I'm going to use a different color like I've been doing. You do whatever you feel is best. So 5, 1. 1, 2, 3, 4, 5, 1. And then 7, 3. And then 8, 1. And connect the dots to form our new triangle. So we've done the transformation, but did the transformation actually preserve congruence? I think instinctively we already know that they're congruent. I could give you patty paper and you guys could trace one of the triangles and move it onto the other and see it. I could show you right here. Oh, mess that up. That again. So I could show you right here that they're perfectly congruent, right? So we know it. But how can we prove it using some ideas that we've explored? Nathaniel, what do you got? I'm sorry?
The distance formula.
How's that going to help us?
We plug it in, we have to measure each side.
And then how would that prove that they're congruent?
Both sides have the same value.
Are you sure? What tells us that that's true? Sort of. Sort of. Well, you're missing the big idea. You're going to kick yourself when you hear it. What will prove the triangle's congruent using his method? Ziamara? Yeah, side, side, side. That's what you're talking about. See, that's a little kick yourself moment. Side, side, side. So he wants to get the distance from here to here, and compare them. Distance from here to here, and here to here, and here to here. Absolutely, we could do that. In fact, part of it's done for us already. Because this is on the grid, horizontally, we can see that this value is 3, and so is this. So we can already see that one side is congruent. But let me show you something else. Because that's a lot of work. I mean, think about it. We got one pair of sides congruent. We would have to do the distance from A to B, B to C, and then A to C, D to E, D to F, and E to F. We already have 2 of them. So we'd have to do 4 more distance formulas. That's a lot of grunt work. We could do it. Doesn't sound like much fun, though. We could do it. But let's be creative and let's explore it in a different way. What could we say? Let me see if I can do this. So what can we say about that side and that side that we could do visually? What could we just look at and say about those two sides? If you're not looking up here and making an effort, then you're going to miss it. Got a few people. Sebastian? The slope is? How'd you figure that out? Okay, so the slope of this one is 1. Let's see, rise 2 over 2. Yeah, so the slope of this one is 1, and the slope of this one is the same. So what did he just prove? What did he just prove? Come on. Well, what if this side does that still have the same slope? It doesn't? You can't tell that it's got the same slope? Rise 2 over 2. Doesn't matter that there's this little, it's still a slope of 1. Is it now congruent though? So the slopes being the same does not prove that it's congruent. But he did prove something else. Come on guys, you guys got to get your brains on. This is where we got to reach to everything that we've learned. Come on, we know this already. This is not new. This is old. Matthew, this is something old. What did we just prove about those two lines? They're parallel. Thank you, Matthew. They're parallel, of course. They're parallel. Maybe there's something we can do with that. Watch this. What if we take this line and I extend it all the way down to here? And what if I take this line and I extend it all the way over here? And I've got this line, which we said was parallel. Let me see if I can get it right. So this line is parallel to this one, and then I extended this line. So let's cover this up for it. So all I did was I kept the same lines, I just extended them, and now I'm going to cover this up a little bit. What could you tell me about this and this? This is parallel to that. I didn't mark it, but we know it to be true. What can you tell me about that angle and that angle? Alexander? They're corresponding, and Stephanie, because they're corresponding, they are congruent. Very good. So we know that this is congruent to this, right? We proved it using the idea of parallel lines. So let's bring back the rest. What if I extend this line? What could you say about this line and this one here? What could you say about those two lines? If you're having trouble seeing this line and this line, what could you say about those two lines? X-Dole, what could you say about those two lines? They're parallel, right? Those two lines are parallel. So if those two lines are parallel, what could you say about this and that? This angle and that angle. What could you say about those two? Alexander? They're congruent because they are they're corresponding as well. So this is congruent to this, and this is congruent to this. What can we say about those two? Stephen? They're congruent. So this is congruent to this because we can prove it using the idea of parallel lines, which came from the slopes being the same. So visually, we were able to prove this. We also knew that this side was congruent to this one. So all we would have to do is find this side congruent to that one, and then we could use side angle side to prove the two triangles are congruent. So we're not going to finish that out because, again, that's grunt work and I don't need to take the time to do that. But the point was that there's a whole other perspective here other than just side, side, side. So you have all that down on your drawing? So that's why some of you are sitting there like just numb, doing nothing, because you're not doing anything. You're just sitting there. I have some people who were involved, volunteering, and I have a lot of people who are just sitting there doing nothing. If you were just sitting there not volunteering, then you were sitting there drawing or doing something, exploring, make a new picture. I don't know, do something. But don't just sit there. That's not getting you anywhere. If you already knew everything, you already knew exactly what was happening, then go on and create your own picture. I don't know what to tell you. But some of you just sitting there, it's just getting you nothing. So, again, we could have taken Nathaniel's approach, used the distance formula and proved side, side, side. But I just wanted to introduce the idea of the fact that we can use other information to prove other things. Okay? So, what we have done is we've proven the two triangles are congruent by using the methods we've learned in our toolbox. And we've proven the transformation was a congruence transformation. So are there any comments or questions? I'll stop saying that because you guys never have any comments or questions. So we'll move on. So, checkpoint number 2. I've already done the transformation for you. I want you to now verify that it's a congruence transformation somehow. So you can't use patty paper, and you can't use a protractor, and you can't use a ruler. You have to use some concept that you've learned over the course of this chapter to prove to me that this transformation that I did is a congruence transformation. And just to make sure we're clear on what the transformation was, it could have been done 2 different ways. It's either a rotation 180 degrees, or it's 2 reflections, a reflection over the y-axis, a reflection over the x-axis, or it could be a reflection over the x-axis and then a reflection over the y-axis. The transformation could have been done 2 different ways. So I did the transformation for you. I want you to verify it and tell me how. How do you verify it? So you got 2 minutes on the clock. Go. All right, take a minute of team talk and see what your teammates came up with. And see if you can come to an agreement on how to prove the two triangles are congruent. Oh, I didn't need you right there. I just meant tell me how to do it.
Just say what you want.
Okay, that's good. Well, there's a number involved and you want the M there. If you're talking about congruent, you don't want that. M refers to a number. If it's a congruency, you want to say oh, A, you wanted to say angle A is congruent A, congruent that A. If you wanted to say the measures were the same, you would say M that A equals. Take some practice. All right. So give me a thumbs up. Give me a thumbs up if you and your teammates agreed on how to prove it. Give me a thumbs up if you and your teammates agreed. Not many. Okay, that doesn't matter. So what'd you come up with? How do you prove it? I'm just looking for overall, what concept do you use to prove it? Let's go to the equity bar since such low volunteer rates. Have something prepared to say. So, student number 13, 15, 9, 4, and 2. Student number 13. SAS. Student 15. SAS. Student number 9. Student number 4. Student number 2. Every single person used side, angle, side, and I did too. I copied what the publisher put, and the publisher put hypotenuse leg. That definitely would not have been my choice. So I went back and I actually changed this, but then I made a mistake and somehow didn't end up here. So I use side, angle, side. Of course, it jumps out at you. You've got this side's distance is 3, so is that. This side's distance is 2, and so is that. And you've got a 90-degree angle here and a 90-degree angle here, side, angle, side. Jumps right out at you. Nathaniel.
I just do SSS.
Okay? So you got the two sides, so all you have to do is figure out the third one. Did you use the distance formula?
Yes.
And did it work out?
Yes.
Great. Anyone do anything different? Okay. So, go ahead.
Angle QRP and angle TR as their vertical angles.
So they're vertical angles, so they are.
Congruent.
So we have angle, side, angle. Beautifully done. You're the first person out of any of my students to bring it up. I'm not sure if someone else did that and they didn't say anything, but you're the first one to bring it up. Beautiful. Great idea. There was somebody else who had a different way of doing it. Anybody else? Any other ways? Okay. So your homework is on page 276, doing numbers 3 through 19 and 29 to 31. It's a total of 20 points or 20 questions because there's no proof. The chapter is finally concluding, and so the next online assignment is to do the interactive practice test that I've shown you over and over again. And your next assessment is actually going to be a quiz, which is tomorrow. And it will be 4.5 to 4.8.